This segment, we're going to talk about sanitary and waste treatment facilities for water. You want to look at it from a simplistic point of view. The sewage from whatever source, whether it be your house or it would be runoff after the rains or from an industry, that's going to go to the treatment plant where it's going to go through primary treatment. And then after primary treatment, we go to secondary treatment, and then finally a tertiary treatment. And oftentimes in the tertiary treatment, chemicals are added. Some of the times the chemicals that are added are to get rid of any pathogens that are there that might have made it through the process. And then the water gets discharged into the local streams or rivers. But by this point in time, it's met certain criteria so that we're not dumping a lot of or hardly any bad waste into those systems. The secondary treatment that we're going to talk about, there can be a number of different ways of handling it. Some of them are called trickling filters, some of them are called oxidation lagoons, and others are referred to as being activated sludge tanks. Any of these three could be used depending on whatever the county or city is doing at that particular point in time. So basically, what sewage is, we pretty much have a pretty good idea, but it's anything that goes down the drain. Now, we're used to thinking about stuff going down the drain at your own house, but it also could be stuff in the industrial world. And some of that can be pretty harsh. If it is, they tend to have their own special treatment for that kind of stuff, but that can occasionally leak. But other examples, besides human waste, we use soaps and detergents when we wash stuff through in our dishwasher or by hand. That, of course, is going to break up in grease and take it down the pipe, so to speak. Food particles, chemicals. We use chemicals for cleaning, like your toilet. Those are going to end up going down. And then there's the occasional goldfish as well. So the purpose of the sewage treatment plants is going to get rid of the organic material, and that's really what we're calling the waste. And so when sewage gets to the plants, it's only about 0.1% that's solid. The rest of it's water or soluble in the water. And what we're trying to do is limit nutrient runoff, because nutrient runoff, it gets into the rivers and streams, and it can cause algae or certain bacteria to grow at a much more rapid rate. And they can end up using up all of the oxygen in the water, so that then fish end up dying, and that's not something that we want to deal with because it's smelly and it's kind of disgusting looking. One of the things that we do is we take a look at the biological oxygen demand of the water that's being treated. And to define what BOD means, it's the oxygen that's needed by microbes to break down the organic material. So the more organic material you have, the more microbes you'll have, and the more demand there is going to be for oxygen. So if you need a whole lot of oxygen, in here the oxygen demand they're talking about in parts per million. If it's 100 or greater, that means that there's a lot of organic material that needs to be broken down. You've got a large number of microorganisms growing in there, and they're using up a lot of oxygen to do it. After the treatment, the BOD will drop, or it may even come into the plant at this lower level, 6 to 9, which is still considered to be poor water quality, because there's still enough organic material in here that we're getting a fair amount of microbial growth. Then when you get down into the 3 to 5 range, it's considered to be fair. The water's moderately clean, but it's still probably not what you would want to be consuming or even discharging. We try to get down to a BOD of between 1 and 2, which is an indication that there's hardly any organic waste. There's nothing for the bacteria to feed on, so there's not going to be a great demand for the oxygen. So in the primary waste treatment, there's two things that are going to go on. There's the mechanical and there's going to be the biological. As one of the videos pointed out, the sewage treatment plant they were looking at had two mechanical separation techniques. One was more for removing larger things, like I believe they use plastics as an example, and other kinds of stuff that's very insoluble. They used a big filter to kind of dredge that out of it. And then they had a finer mesh that got smaller particles, grit, and that sort of thing. And so that most of what was going through would be soluble material in the water. So when you do that, you end up getting this insoluble material that they refer to as primary sludge, and they're going to let that settle out. In some places, the water and all the soluble stuff will go into a tank, and then they'll add something to it that will cause suspended insoluble material to settle down more quickly, that sort of thing. What will happen then with this primary sludge is it's allowed to dry, and then it's going to get ground up and can be used as fertilizer. In some cases, it goes to an anaerobic sludge tank where anaerobic bacteria, and if you remember what anaerobic means, an means without, aerobic means air, so these are organisms that are going to grow without the presence of oxygen. So they don't need to have, they just let it sit around and let the microorganisms do their work. They don't have to add air or anything like that to it. And then the solids get dried and disposed of. It can be used as fertilizer. They make sure that the pathogen count is very low or next to nothing. Oftentimes they'll compost it where you can use heat to kill some of the microorganisms and stuff, so that when you're using this as fertilizer, you're not dumping pathogens out on the field. The liquids from this primary waste treatment are going to go to the secondary treatment. And what happens then is bacteria in the process are going to do a process that's called mineralization. You're going to get the biological material being broken down to even smaller components utilized by the bacteria. But in this process, this is aerobic bacteria doing this process, and so air will be pumped into this secondary treatment tank constantly to give these organisms the amount of oxygen they need to grow and do what they need to do. In some places, when you're dealing with very large amounts of water that may have some toxic stuff that you're really concerned with, they might use an oxidation lagoon where they pump all the water in there. It's held for months and give the bacteria a chance to break down the organic material and give any of the special bacteria a chance to break down any toxic metals that may have gotten in there. So oxidation lagoons tend not to be used by municipalities. Trickling filter systems. So the trickling filter system is one in which you have a number of components that create a very good filter, and the water from the primary treatment is going to be spread out all over the surface. And they showed that in some of the videos. They were doing it more of a small scale, but you can do this at a large scale. And inside this filter, you have a solid support that has bacteria growing on it. And they've actually formed something that we call a biofilm. So it's going to be a layer of a bunch of different bacteria. It could have some protozoa and some other organisms in there. They're going to help to get rid of even more contaminants within the water. Microorganisms work really efficiently, and so they're able to actually remove more stuff than we would necessarily chemically. Because they are formed a biofilm, they pretty much stay in place. So all the liquid water goes filters through, and then contaminants are removed, and then when the water gets down to the bottom, it exits the filter system and is fairly clean at that point in time. This is just kind of a micrograph of what you might find in these plates. You can see some of these long, thin microorganisms in there. It's just sitting around waiting for the water to get to them with all the nutrients. The third kind of secondary treatment could be the activated sludge tank. Again, in this one, oxygen is being added because we're working with microorganisms. These things tend to rotate through the tank with air being pumped into it, so we're constantly aerating it. Then we have some other form of aeration as well, just trying to make sure that it gets the air that it needs. So then at the end of that, we've reduced a lot of organic material. We've got a pretty low BOD, but now we're ready to discharge the water, and we want to make sure that we're not discharging pathogens out into the environment. And so what a lot of times water treatment plants will do is they'll use chlorine gas, which is very effective at killing pathogens. It will kill non-pathogens as well, but pathogens tend to be a little more fragile for some reason, and they're a little bit easier to kill. And that's the main reason for using something like chlorine gas. Also, in the tertiary treatment, microbes or chemicals might be used to remove phosphate and nitrogen. Both of these can contribute to algae blooms and other issues of discharge. So we're trying to get rid of this material as well. And the phosphate and the nitrogen itself may or may not be organic in nature. So here is a schematic of what might be happening with using microorganisms to remove the nitrogen. You add the water, which they call the influent, and you have the nitrification bacteria breaking it down, and then the next bacteria in line is going to do some denitrification, and that releases nitrogen gas. So now the nitrogen's back in the atmosphere and not being used for the growth of other organisms. And then finally some oxidation bacteria may be in there to break things down, like methanol in the presence of oxygen, and produce carbon dioxide. So at that point in time, the BOD is going to be very, very low. We're looking at 1 to 2 parts per million. And that's what the regulations tend to be before they can be discharged into the environment. If they have a higher than that BOD, they have to go back and retreat it until they can get it down to that point in time. Question is, can it be used as drinking water? Well, at this point in time, maybe not the best, but it could then be taken through the process of how we would purify drinking water. We've gotten rid of the pathogens, we've gotten rid of the phosphates, we've gotten rid of the nitrogens, and we've gotten rid of all other organic compounds. So it is fairly decent water, but probably not the point where we actually want to use it for drinking just yet. Here's a schematic, very similar to the one I had in the very first slide on the previous presentation. Here you have the treatment plant. Here they're talking about using a pretreatment with hydrogen peroxide. That's going to kill some microorganisms, especially anaerobic bacteria, which we do have in our intestinal tract. And then it goes through the primary sedimentation. The solid part's going to be pumped out and go through gravity thickening and eventually become fertilizer. Here they're talking about putting it in the form of pellets, whereas the effluent is going to go through the secondary reactors. There's going to be a secondary sedimentation. Again, that can end up in the fertilizer plant as well. And then they're instead of using chlorine gas, they're using bleach. Sodium hypochlorite is basically bleach, and they're using that. And then they use sodium bisulfite, which it activates the chlorine, and then it's ready to be discharged.